Yes, can you? Okay, excellent. So now we're going to have our second speaker for today. We have Andrew, and he's going to talk us about some heterogeneous mean field limits.
Hello, thank you for coming. Yeah, before I actually get into it, I want to admit that most of this is not actually my work. I'm going to talk about how it applies to my work, but I wanted to thank Pierre-Emmanuel, Jabin, and Fabio Coppini, who are the people that wrote the papers on this, and Natalie Ayi, who wrote a really nice review paper on heterogeneous mean field limits in general, and of course my supervisors. So the whole thing's going to be about interacting particle systems. So this is basically any system where you have individual agents or neurons or trees, and they interact by taking an average of their interactions with every other agent in the system. Specifically, I'm interested in modeling opinion dynamics. So the state space is the opinion of person I, and that evolves according to interactions with every other person J. There's this function phi that determines how much two people are willing to listen to each other based on the distance between their opinions. The idea being that if your opinions are closer, you're more likely to listen to someone. And then that's times by the distance so that you move towards that person's opinion. And the type of dynamics that you get depend on what type of thing you put in for this interaction function here. So in this one, it cuts off after some distance, and your population splits into clusters that stop interacting. In the middle one, it's exponential, so people always interact at least a little bit, and so eventually everyone agrees. The idea behind, so I'm first going to talk about normal mean field limits, and then I'll talk about heterogeneous mean field limits. The idea behind normal mean field limits is that rather than plotting people's trajectories over time, we could look at the density of opinion in the population. So this is a bigger simulation with 20,000 people, and at various time steps, I'm plotting with opinion on the x-axis, the density of people with that opinion. And the idea is that this looks like it behaves quite nicely. So we can define something called the empirical density. So starting off with our ODE system, we place a Dirac measure at the opinion of each of the people in our system, which is not quite the same as this histogram. We are basically placing a point mass at each person's opinion. And the idea is to try and find some PDE that is satisfied by this opinion density. The trick to do that is that if you integrate this empirical density against some function, you get back the function evaluated at each of the people's opinions. And this lets you do this. So I'm not going to explain all of it, but in like way up in the top left, we start off with the time derivative of the density integrated against some test function. We do a lot of swapping back and forth between the empirical density and the sum. There's a chain rule and an integration by parts, and at the end, you get the same test function, but now integrated against a spatial derivative of something messier. And since this is true for an arbitrary test function, it basically means that these derivatives have to be the same. So we get a PDE that is satisfied by the opinion density. This is nice because we now have one PDE rather than a huge number of ODEs. And basically this PDE is kind of the limit as you take an infinite population size in your ODE model. You can also do this with noise. You basically get exactly the same thing here, but you add on some diffusion. So if in your SDE people's opinions are moving randomly slightly, you get some diffusion in your PDE, which basically just spreads out your opinion density slightly. If this looks like a Fokker-Planck equation, it's because it is, but for a single particle that interacts with its own opinion density, which is called a McKean-Blasov SDE. So some examples of what this looks like. So yeah, for opinion dynamics, as an SDE, we have this same sum over interactions for the deterministic bit, and then just some noise on the end. And so when we take this mean field limit and look at the density instead, rather than having a sum over interactions with other people, we have an integral over interactions with other opinions, and we times by the density at the opinion that we're interacting with. So rather than summing over the people and asking what their opinions are, we ask what the opinions might be and what proportion of the population has that opinion. And then our noise on the SDE becomes some diffusion. Oh, boundary conditions. Yes, the SDE has reflecting boundary conditions at plus or minus 1 for the opinions, and those become no flux boundary conditions on the PDE. So this is an example of the kind of thing that you get. So this is using a bounded confidence interaction function. So the interaction function phi is 1 if your opinions are closer than 0.8, and it's 0 outside of that. And because 0.8 is relatively big, basically, we get one large cluster in the middle. If we were to add more noise, we would have more diffusion, and this cluster would be sort of more spread out. If we decrease the interaction radius, people are less willing to interact, and instead we get two clusters. And if we decrease it even further, this scale on the left-hand side now is very close to a half all the way through. So we're getting something that looks quite similar to being uniform. We get a little bit of clustering at the edges because the people with a really extreme opinion, say a +1, there's no one above +1 for them to interact with. So they're only interacting with people that have a lower opinion, which is why you get some clustering at the edges, but mostly it's kind of uniform. This is basically saying that if you have a big enough, a very big population, but people aren't willing to interact with each other, then people's positions are just sort of random, or their opinions are sort of random. So the heterogeneous bit. I'm more interested in opinion dynamics on a network. So I'm going to add in this Wij to the ODE that describes the extent to which person I and j interact with each other. And it makes your dynamics a bit messier. So this is the network that we're using. It's an Erdős-Rényi random graph. And if we look at the bounded confidence interaction function, we still get clustering, but we get a different number of clusters than without a network. And it's kind of a bit more unpredictable as to who is going to end up in what cluster. In particular, for these people at the top with a very extreme opinion, they're only connected to a handful of people in the network, and they've got a very extreme opinion, so none of the people they're connected to actually want to interact with them. So they end up not changing their opinions at all. The exponential one still gives you consensus because the network is connected, so people eventually interact with each other at least a little bit. But the idea is that we want to take a mean-field limit of this type of system, including information about the network. This little bit on the left here is just to say that you have a choice to make as to whether you just divide by the total population size or the number of people that you're connected to. It kind of depends on what you interpret the network to mean. If you interpret the network to mean you could interact with anyone, but then the network says who you would listen to, then it makes sense to divide by everyone. If the network says the people that you could possibly interact with, then it makes sense to divide by the number of people you could possibly interact with. I'm going to stick mostly to this top one because all the mean field stuff is done with a 1/n scaling because it's a lot easier. So the problem with going to this mean field limit is that when we have a network, we can have different networks, and these will evolve in different ways, but they have the same opinion density. So it's not enough to know the density of opinions in the population. We also need to know who has what opinion to determine who is going to interact with each other, to find out how that opinion density will change. And this is called non-exchangeability. So we can't swap two people. We can't swap two people and expect things to basically be the same. So the first thing we can do is just, in this picture, the heights are just kind of random, but we can order people by their index. So index 1 up to n is 5. And then we can introduce a new variable, psi, and psi I is going to be I over n. So person 1 now has index 1/5. Person 2 has index 2/5 up to person 5 having index 5. Oh, 1, sorry. Basically, this scales the indexing to something that is always between 0 and 1. And basically, as we add, if we were to add more people to this system, we would still get to this index variable psi being between 0 and 1. The idea being, if we add infinitely many people, this index then becomes dense in 0, 1, and basically becomes continuous if we added infinitely many people. But we divide by n so that it always stays between 0 and 1. We can actually think of this now as a density over opinion and index space. So now placing a point mass at each of these 5 points gives us a probability density over opinions and indexes. We also need to keep track of the network somehow, so we can define this function, Wn, because we have n people at the moment, that is going to be piecewise constant. And basically in each section, we set the value of the function at psi I, psi j, so the indexes of person I and j, to be what the network value is for people I and j. So this Wn is a function that contains the same information as the network. So if we swap some people around, but keep the same opinion density, then our joint density over opinion and index space changes. And basically this joint density over opinion and index has enough information to tell you how it will evolve, if you also know how different indexes interact with each other. So when we take infinitely many people, this becomes a nice smooth density, and this becomes a sort of proper function here. So the idea is that this is sort of representing the limit of the network as it becomes very, very large. And this is representing this density in opinion and index space. So the PD gets a bit nastier, but not that much nastier. So previously we just had a density over opinions, and now we have a density over opinions and indices. Previously we just had interactions with other opinions, and now we have interactions with other opinions and other indices. So this basically says you're looking at, you have opinion X and index psi, and you're looking at a different person that has opinion Y and index zeta. And you're asking, how much does my opinion, how much will I listen to their opinion, and how much am I connected to that person? So you're interacting across different opinions and also across the index, which is kind of interacting across the network. Oh yeah, this thing W is called a graphon that describes how different parts of this index are connected to each other. So some examples. We're going to use the same bounded confidence interaction function with a relatively small radius of 0.3. I'm going to use this graphon here. This is kind of a limit of a Watts-Strogatz type network. So if your indices are very close, then this dark color indicates you are likely to be connected. This is done mod 1, so kind of people are in a circle. And if your indices are a bit further apart, then you're less likely to be connected. So this is kind of a small world type graphon. You're mostly connected to the people that have a similar index to you, but could be connected to people anywhere. And I'm going to say that the initial density depends on your index. So this is your index. Oh, I'm not going to access that. Sorry, this should be opinion space from -1 to 1, and the height is the density. So this says that people with a low index are more likely to have a negative opinion, and people with a high index are more likely to have a positive opinion. And then it will evolve over time. So if you look just at the opinions, then you sort of have clustering in opinions in the same way that you did before, except now your clustering depends on your index. So at this final time here, people with index, a small index, are still more likely to have a negative opinion, but that negative opinion is now more clustered. And people with a positive index are still more likely to have a positive opinion, but that is again more clustered. And there is some interaction between clusters at different indices. So different parts of the network have different opinion densities, basically. So for the next example, I'm going to keep the interaction function the same, keep the graphon the same, but just start with a flat opinion, a flat density. So this basically says that if you think about the finite number of people case, for each person, you give them a random index, so a random position in the network, and a random opinion. So you're just sort of starting off completely randomly. And in this case, you don't get any variation between the indices, which basically means that all the parts of the network are exactly the same. It sort of makes sense. All the parts of the network start off the same, and all the parts of the network stay the same. But what it really means is that it doesn't matter what this graphon is. It doesn't matter what the network structure is. where people are in the network has absolutely no effect on what their opinion density is. So you could change this graphon to be something completely different. You could have like the limit of a power law network, or you could have a limit of an Erdős-Rényi network, and it wouldn't make a difference what you put in for this graphon on what happened in the dynamics. You would still get exactly the same thing, which is kind of a problem for me, because what I wanted to look at was evolving this in time, and it turns out it doesn't make a difference, so it's kind of pointless to evolve it in time. So why does this happen? So we started off with an opinion profile that was the same at all the indices, and it turns out that for this graphon, if you integrate it along a slice, you basically get the equivalent of a person's degree in the network. And that is constant across the graphon. So basically all the parts of the network have the same degree. And that's the thing that causes you to not create any heterogeneity. So the graphon structure isn't important because the opinion distribution is the same everywhere, which also means that the opinion distribution that we get is the same as the classical mean field limit. So basically the network did absolutely nothing. This distribution here that we get that is the same across all the indices, if we had just solved the simpler PDE with no network, we would get this exactly the same shape. So yeah, if the expected network degree and the initial opinion profile don't depend on the index, then the heterogeneous mean field limit and the classical mean field limit are the same. Yes, there are some actual papers that prove this type of thing properly. And you also get a similar effect if you divide by the degree, which I mentioned earlier. You're sort of ensuring that the degree will always be the same across the network because you're dividing by it. And yeah, the people that wrote this paper commented at the end that it's a really unsatisfying result because it's not actually useful for large networks. It's useful when your network is actually in the limit as your network becomes infinite. But if you pick a very, very large network, the adjacency matrix probably doesn't look like the graphon. So for example, here, if you took an Erdős-Rényi random network where people are connected independently with probability P, you would get exactly the same behavior as a fully connected network, no matter what the value of P is. And that's obviously not going to be true for any finite network. If you pick a finite network and choose a value of P that's really, really small, that network can be very sparse, but the behavior that you get in this limit is exactly the same as if it was a completely fully connected network. So yeah, the usefulness of doing something like a mean field or a heterogeneous mean field limit really depends on what it is that you are trying to model. In our situation, we're always assuming that people's initial opinions don't depend on the network, and we're always dividing by the degree. So for us, it's sort of never really worth taking this heterogeneous mean field limit. But if you looked at something where the initial degree, the initial opinion profile is different at different points in the network, then this heterogeneous mean field limit would be useful. And I guess my final point that is a SPAAM talk is a nice opportunity to present something that you read a lot about but didn't use. And just to plug us at the end, this seminar is organized by the SIAM student chapter, and we have all the social medias. Feel free to follow any of them. Thank you.